Hello students, today we are going to see the lesson current electricity and we are going to see the session 3, and in this topic we are going to see this topics for today. Hope you understand, and let's go to the today's session. First of all, let me start with the Kirchhoff rule, and this is the important rule which is used in most of the electronic systems. Actually, Ohm's law is useful for simple circuits. For more complex circuits, Kirchhoff's rules can be used to find current and voltage. There are two generalized rules. One is Kirchhoff's current rule, which is called as first rule, and Kirchhoff's voltage rule, and it is mentioned as Kirchhoff's second rule. First of all, let's start with Kirchhoff's first rule, which is current rule or junction rule. Actually, this rule states that an algebraic sum of the currents at any junction of a circuit is 0. Let me give one example for you. If you see a electric post in our street, you can see lot of connections are there like this. Is it so? Yeah, this is the post. Okay, this is your house connection and next house connection and some other house connection. There are several connections are in one light post. Okay, just imagine if all the houses are taken to phase current, then each and every houses are allowed to current mostly of 230 volt, but we cannot use the full 230 volt at a time in our house. So we have to return the current. That means the government or the EB board allowed for 230 volt for us to acquire on that particular time, but we are not ready to acquire that 230 volt at that particular time. So we take only 60, 70 or 100 volt and we left the current in that same line. Remember, if you do that again and again, what will happen? The reverse current in that area and the reverse current which is in that post will make a big damage. Okay, but that's not happening here. All the houses which are nearby you will reverse the current which they are not used, but there is no problem in the circuit of the post, electric post. See why it has to be happen, but it's not happening in the post. Why? It's all because of this rule, Kirchhoff's rule. That is the algebraic sum. All together, the full 5 or 6 connections are totaling, and they are called as algebraic sum of the currents at any junction. This junction of a circuit is 0. It equals all the other currents. Let me give some examples for this. All charges that enter of a given junction in a circuit must leave that junction, since charge cannot build or disappear at a junction. Okay, so current entering the junction is taken as positive and current leaving the junction is taken as negative. So after the usage, we left the current to the same electrical post as negative. Negative will not make any impact in the circuit. So applying this law to the junction A, we get, see, this is I1, I2, I3, I4, I5, and imagine this is your house and your neighbor's house. Okay, you are sending the current written, and in that, according to Kirchhoff rule, it is taken as I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. So this I1 and I2 will equals the I3, I4 and I5. Okay, like this, the current in each and every house's circuits are equal with other circuits. So the currents at any junction is at 0. Now let's see the Kirchhoff's second rule. And it's called as voltage rule or loop rule. It states that in a closed circuit, the algebraic sum of the products of the current and resistance of each part of the circuit is equal to the total EMF included in the circuit. Let me show one. Which is going A to B. Okay, this is going A to B, and this is going B to A. Here the voltage is equal to plus IR, and here voltage is equal to minus IR, and here the going to A to B. Voltage is equal to minus plus pi psi, and this is voltage equal to minus psi. Suppose if the direction of current is opposite to the direction of the loop, then the product of current and voltage across the resistor is negative. The EMF is considered positive when proceedings for the negative to the positive terminal. Let me give one other example for you. See, in every houses, as I mentioned earlier in the parallel circuit of parallel resistors or parallel conductors, every house has to develop a different current circuits in their electrical panel, because each and every rooms require a different electrical appliances. See, you cannot use your fridge or your washing machine or your mixie or grinder in a hall. Okay, so you have to have a separate connection for that in a separate room. That's why we use the mixie or grinder in our kitchen and the washing machine in our nearby bathrooms, and we use the TV and AC in the living rooms. So the current connection has to be separated as it is in the board. That's why the Kirchhoff's second rule states that the circuit and the closed circuit and the algebraic sum of the products of the current and the resistance of each part of the circuit, that means resistance and the conductors of the each and every rooms, is equal to the total EMF included in the circuit. They are concluded as a full circuit after the connections, but in between the rooms the requirement and the passage of currents are different. They are not equal. Even though we have only 2 rooms, we have to differentiate the current as it is according to the requirement of that room. So Kirchhoff voltage rule has to be applied only when all the currents in the circuit reach a steady state condition. This is what very important in that. Now let's see the conditions for bridge balance in Wheatstone bridge. Students, this is a very important question, and which they have to ask this very frequently in examinations. So let's move to this. An important application of Kirchhoff's rule is the Wheatstone bridge, and it is used to compare the resistance and to determine the unknown resistance in an electrical network. Now let's have consist the four resistance we use here. They are P, Q, R and S as I shown in the figure. Now a galvanometer G is connected in between the points B and D. The battery is connected between the point A and C. Let me show. This is the Wheatstone bridge connection. P, Q and R, S are some resistance. A and C are connected with the positive and negative terminals of the battery and whichever EMF of psi, and current I1 to P and I2 to R, I3 to Q and I4 to S. Now let's see what's the current movement. Let I1, I2, I3 and I4 be the currents through various branches and the current through the galvanometer Ig and its resistance is G. Okay, capital G. First one, let us apply the Kirchhoff's first rule to the junction B. We are going to apply the Kirchhoff's first rule to the junction B. See, we are giving a current I1 which is plus, but here in this terminal it has been divided into two segments. One is Ig and another one is I3. Okay, while having a positive current here, it loses its positive and it gives to I3 and Ig. So I1 minus Ig minus I3 is equal to 0. Second, applying the Kirchhoff's first rule to the junction D. Here we receive current, positive current from I2, and at this terminal we receive the positive current from G because it already received the positive current from I1, and so Ig have a positive current, so we add I2 plus Ig and it gives current to I4, this circuit. Okay, so we put minus here. If you have any doubt in this terminals, kindly check with me because it's very easy question, but you have to understand properly. Now, applying Kirchhoff's second rule to the loop ABDA. What is the loop here? A, B, D and again A. First half cycle of this Wheatstone bridge, A, B, D and again A. So what are the currents here? First one is I1P and the second one is Ig into capital G and I2 into R. Here this I1P and IgG are positive, but we lose current at I2, so it is minus I1P plus IgG minus I2R is equal to 0. This is equation number 3. And the fourth one, applying Kirchhoff's second rule to loop A, B, C, D, A. So A, B, C, D, A. Full terminal and all the four diodes we use here. So I1P and I3G, we give I1 current and it also get from I3. So I1P plus I3Q minus I24, here we lose current and again we lose current here at I2R. Okay. When the points B and D are at same potential, then there is no potential difference between B and D. So no current flows through the galvanometer Ig. So the Ig is equal to 0. If you substitute the value of Ig equal to 0 in equation number 1, 2 and 3, we get I1 is equal to I3, equation number 5, I2 is equal to I4, equation number 6, I1P is equal to I2R, which is termed as equation number 7. Now substituting the equation 5 and 6, and in equation number 4 we get, if you substitute the values of I1 and I2 in equation number 4, we get I1P plus I1Q minus I2S minus I2R, which is equal to 0. So I1P plus P plus Q and I2 R plus S, which we take I1 as common here and I2 as common here, and equate this equation left and right. Now dividing equation 8 by equation 7, we get P plus Q by P, which is equal to R plus S by R. That is dividing this one I1 and this I1. So we get P plus Q by R, P, and dividing I2 here and I2 here, so R plus S by R. Taking P as common, so 1 plus Q by P or 1 plus S by R, then we can neglect both I1 and 1 here, so Q by P is equal to S by R, or P by Q is equal to R by S. This is the bridge balance condition. Under this condition, galvanometer shows null deflection. Next one is meter bridge. Remember students, meter bridge is a practical examination question also. Okay, so understand this meter bridge up to your level. We have to study this for a 5-mark question in theory and a practical examination question, that is 30-mark question. So take more care while seeing this video. Now let me introduce this meter bridge connection and explain before I start. See, this meter bridge connection have two resistance. One is unknown resistance and another one is known resistance. Usually I explain students to remember this as a two guns, okay, because it looks like guns in between a plate. The connection is between A and B, and in the terminal G1 it is one positive and one negative, and in terminal G2 it is one positive and one negative. It has a one middle connection which is connected with a galvanometer to the high resistance. Then here we connect with the jockey. Actually the length of the meter bridge is 1 meter, which is termed as L1 from here in increasing mode and L2 in decreasing mode. Now we connect the A with a battery. Usually we use Leclanche cells for this meter bridge, and a key which is connected with the A and B. Now let's move into the theory part. See, meter bridge is another form of a Wheatstone bridge. It consists of a uniform manganese wire AB of 1 meter length. Usually we use manganese wire here from A to B, or sometimes in some practical examination we use the wire copper instead of manganese. The wire is stretched along a meter scale on a wooden board between two copper strips, that is C and D. Between these two copper strips, another copper strip E here is mounted to enclose two gaps G1 and G2. An unknown resistance P is connected. This is an unknown resistance. You might have 1 meter length of a wire, okay, steel wire or a manganese wire of 1 meter length. Particularly its radius is about 0.2 × 10⁻³ meter. An unknown resistance P is connected in G1 and a standard resistance Q is connected in a G2, because in Q we have a jockey, which is a conducting wire, is connected to the terminal E on the central copper strip through a galvanometer and a high resistance HR. The position of the jockey on the wire is adjusted so that the galvanometer shows zero deflection. See, here our main part of the work is to receive a zero deflection in the galvanometer. Okay, if the circuit and the passage of current and everything is correct, then you can get a zero deflection in the galvanometer. If it is not possible, then there must be a problem in your meter which circuit, or there is a problem in your connections. So remember, if you are not getting a galvanometer of zero deflection, then your circuit is wrong or your current deflection is wrong. Now let the point be J. The Leclanche cell and the key K are connected across the ends of the bridge wire. The lengths AJ and AJB, that means the length from A to jockey and length from jockey to B of the bridge wire, now replaces the resistance R and S of the Wheatstone bridge. Then P by Q, that means the unknown resistance divided by the known resistance, and the resistance R divided by the resistance S, which is equal to R dash AJ, that means the length from A to J and the length from J to B. Here R dash is the resistance per unit length of wire. Therefore P by Q is equal to AJ by JB, which is L1 by L2, and P is equal to Q into L1 by L2. Here we divide the length of the wire from A to J divided by the wire J to B. By interchange P and Q, you can interchange the resistance P, then the unknown resistance P and the known resistance Q. The error due to the N resistance can be eliminated by this, and the average value of P is found using this interchange method. To find specific resistance of the material of the wire in the coil P, the radius R and the length L of the wire is measured. Now the specific resistance or resistivity rho can be calculated using the relation. Let me give resistance rho divided by L by A, length by area. By rearranging the above equation, we get rho is equal to resistance into A by L. So we have to find the resistance, then we have to put by divided by area by length. While doing that, we get, if P is the unknown resistance in the equation 4, then it becomes P rho is equal to P into pi r square by L, which is referred to the area, pi r square. Students, next we are going to see about the potentiometer. Potentiometer is used for the accurate measurement of potential differences, current and resistance. Actually, it consists of 10-meter long uniform wire of manganese or constantine stretched in parallel rows and each of 1 meter length, and they are, the wires of 10 meter are in a wooden board. See, there are two ends, one is C and another one is D. In between that we have 6 switches, one is M1, another one is M and another one is M2. In the right side we have N1, N and N2. All the 6 switches are connected in a switch which is called DP-DT switch. Okay, now we have two cells. One is Leclanche cell which is Psi1 and another one is Daniell cell, it is Psi2. The portion M is connected with the point C and the C is connected with the battery of its positive terminal. The negative terminal of the battery is connected with the key and then it's connected in the lower part of the rheostat. Then if you come to N, this N is connected with the galvanometer to find the current deflection and high resistance, to measure or to minimize the resistance. Then it is connected with the jockey. This experiment of potentiometer is used to compare the EMF of two cells, and the circuit connections are made as shown in figure. The potentiometer via CD is connected to a battery BT and the key K which are in series. Okay, now this is called as a primary circuit. The end C is connected to the terminal M as I told you, and this terminal is called DP-DT switch, double pole double throw switch. The other terminal N is connected as I told you with the galvanometer and the high resistance HR. The cells whose EMF Psi1 and Psi2 to be compared. Okay, we are going to compare the EMF of this Daniell Leclanche cell Psi1 and the Daniell cell Psi2 through the connected terminals of M1, N1, M2, N2 using the DP-DT switch. Now the positive terminals of battery Psi1, Psi2 should be connected to the same end C. Then the DP-DT switch is pressed towards M1, N1 so that the cell Psi1 is included in the secondary circuit. That means here we operate this system with the Leclanche cell because we connected the Leclanche cell with the terminals M1 and N1. Now the balancing length L1 is found by adjusting the jockey for zero deflection. Then the second cell Psi2 is included in the circuit and the balancing length L2 is determined. Remember, L2 is connected between the M2 and N2 and the cell connected here in between these terminals are Daniell cell. Let R be the resistance per length of the potentiometer wire and I be the current flowing through the wire. So we have Psi1 is equal to IRL1 which is termed as equation number 1, Psi2 IRL2, it is the equation number 2. Now by dividing equation number 1 by 2 we get Psi1 by Psi2 is equal to L1 by L2 because both this I are cancelled. Both I are cancelled. So by including a rheostat in the primary circuit, the experiment can be repeated several times by changing the current flowing through it. Now let's see another experiment using this potentiometer. measurement of internal resistance of a cell by potentiometer. This experiment is used to measure the internal resistance of a cell. The circuit connections are made as shown in the figure. Right? Here in this experiment, the end C of the potentiometer wire is connected to the positive terminal of the battery, which is termed as BT, and the negative terminal of the battery is connected with the key, then and its end is connected with the terminal D using the key 1. This forms the primary circuit here. Now the positive terminal of the cell psi is connected to the end C of the wire. Here this positive terminal psi is connected with the end C. The negative terminal of the battery, this is connected to a jockey through a galvanometer and a high resistance, and also a resistance box R, which is an external resistance, and the key K2 are connected through the cell psi. With key K2 open, the balancing point J is obtained and the balancing length Cj is equal to L1 is measured. Since the cell is in open circuit, its EMF is psi proportional to L1, and with the help of the resistance box, which is external resistance R, which is introduced, say R and the K2 is closed. Now the current passing through the cell and the resistance R is given by I is equal to psi capital R plus small r. Here this capital R refers the resistance which is connected external, and this is small r referred the connection in internal. Now the potential difference across R is V is equal to psi R divided by capital R plus R. When this potential difference is balanced on the potentiometer wire, let L2 be the balancing length, then psi R divided by capital R plus R is proportional to L2, which is termed as the equation number 1. So if capital R plus R is divided by R, then we get L1 divided by L2. If you take 1 plus small r by capital R, we get L1 divided by L2. So if you take small r one side and all the other terms to the right hand side, then small r is equal to capital R into L1 by L2 minus 1. This 1 to this side as minus. Now small r is equal to capital R into L1 minus L2 divided by L1. I think you know about this LCM. And substituting the values of R and L1, L2, the internal resistance of the cell is determined, because we know what is the resistance in the external circuit. It's properly, and it has to be defined by the person who is doing the experiments. And we also know by using the jockey we can find out the lengths L1 and L2. So the internal resistance of the cell can be determined using this experiment. The internal resistance of the cell is not constant but increases with increase of internal external resistance connected across its terminal. If you raise the value of capital R, then the internal resistance is raised. Thank you, students. Thank you for your patience. Study well.